أنا دكتور خالد وليد، ربان سفينة النجاة إلى شواطئ بكة القدس. I am Dr. Khaled Waleed, the captain of the ship of salvation to the shores of Baka, Jerusalem.
Okay, let's start with a question for you. What if the universe was much older than we think? And what if its building blocks were something incredibly familiar, like water?
That's quite the hook. And it sets us up perfectly for today's deep dive.
Exactly. We're looking at some fascinating source material one of you sent in. It's called Cosmic Water by Dr. Khaled Waleed.
Today, we're looking into something really groundbreaking that landed on our research desk. The totally new way of seeing the universe, called the Cosmic Water Model.
That's right. We've been digging into this, and, well, it puts forward some radical ideas, a very different age for the universe, and maybe a fundamental source we weren't expecting.
Okay, let's just jump right in and unpack this. So the Cosmic Water Model, it kind of throws a curveball at what we think we know in two big ways. First, it's saying the universe isn't 13.8 billion years old, but actually 24 billion years. That's a lot older.
A lot older, nearly double.
Yeah. Think about what that extra time might mean. And second, and this is where it gets really interesting, it suggests a primordial kind of water is the source of, well, everything. Matter, energy, space, time, the works.
It's incredibly ambitious. The model tries to be this comprehensive framework, pulling from different scientific fields, aiming to be a testable alternative to current cosmology.
Right, not just tweaking things, a fundamental rethink.
Exactly.
And look, when you first hear 24 billion-year-old universe from water, it sounds, well, maybe a bit out there.
Understandably so.
But here on the deep dive, that's what we do. We explore the source material, look at the arguments, the evidence presented, and see what insights pop out, ready to dive in.
Absolutely. So this cosmic water model, it starts with a few core assumptions that right away make it different from the standard model.
Go.
First, as you said, the age. 24 billion years. That's huge. And that extra time, as we'll get into, might actually help with some current puzzles in cosmology.
A massive difference, yeah. What's the basic reasoning for going that much older?
Well, the model posits that right at the very beginning, there was this fundamental stuff called cosmic water. Now, it's crucial to stress this isn't like the water in your glass.
Right. Naughty Joe.
No. It's described as a primordial state, like a super energetic plasma maybe, packed with quantum energy, and it had properties like hydrogen and oxygen, but somehow unified.
Okay, so something way more primal. Must have been incredibly powerful right at the start.
Oh, absolutely. The theory talks about the universe's very first moments, Planck time, that's like 10 seconds after the theoretical start. Incredibly tiny fraction of a second.
Wow.
And at that point, cosmic water supposedly existed as this unified energy state at an unbelievable temperature, something like 10 Kelvin.
That's, yeah, mind-bogglingly hot. Hard to even imagine.
It really is. And the story doesn't stop there with just our universe's birth.
No.
No. One of the more, let's say, speculative aspects is this idea of a cosmic cycle, that cosmic water might somehow be recycled across multiple universes.
Okay, so hinting at a much grander, maybe eternal kind of process.
Potentially.
All right, so we've got older universe, 24 billion years, originates from the super hot, super energetic, primordial, water-like stuff. And maybe it's part of a cosmic recycling system. That's a big picture shift. Now let's zoom in. The theoretical framework, what is cosmic water, according to the model?
Okay, so definition-wise. First, it's seen as embodying quantum energy. They draw a parallel to the inflation field.
Ah, the thing that supposedly drove cosmic inflation in the standard model.
Exactly. So cosmic water takes on that role here. It's the engine behind that initial, very rapid expansion.
Okay, so it does the job of inflation, but it's this water-like entity, not just a field.
That seems to be the core idea, yeah. Second, it's described as having a primordial molecular structure, like a unified state where hydrogen-like and oxygen-like properties are linked, maybe as fundamental quantum particles or some really exotic state.
Unified hydrogen and oxygen.
Yeah.
That's a tricky concept.
Yeah.
What properties would this stuff need to have?
Well, they propose a few key things. It had to be stable under those insane initial conditions, the heat, the density.
Right, 10K.
Yeah.
Right.
Then, crucially, it needed the ability to transform into everything else. Matter, radiation, space-time itself. They call this cosmic water transformation.
Okay.
And then there's this intriguing idea of cosmic memory, which somehow ties into its potential for recycling across universes. Though, you know, the how of that is very much theoretical at this stage.
Cosmic memory. Yeah, that sounds like something for way down the line. Okay, so we have a sort of definition. How does it actually make a universe? What's in the mechanism, this cosmic water transformation?
They lay it out in 3 phases. Phase 1, primordial creation. This is right at Planck time. The singularity in this model wasn't just a point, it was cosmic water in that unified energy state.
Okay.
Then, through some kind of quantum transformation driven by the extreme conditions, this cosmic water released its energy.
Released it into what?
Into the fundamental particles, quarks, electrons, things like that. Also into radiation, like photons. And crucially, into the expansion of space-time itself.
So it drives the expansion and creates the initial particles, kind of like inflation plus reheating in the standard model, but all from cosmic water.
Pretty much, yeah. The source is different.
Okay, phase 2.
Phase 2 is called aquatic nucleosynthesis. This runs from about 10 nanoseconds up to maybe 100 seconds. During this period, which includes the inflationary burst, cosmic water is said to transform into primordial hydrogen and oxygen, but as quantum particles initially.
And these H and O particles then?
After inflation settles down a bit, they interact to form the light elements, mostly hydrogen, helium. It's similar to Big Bang nucleosynthesis, but the model suggests it might have been a more drawn-out process because of the whole cosmic water transition.
More drawn out. Fits with the older universe idea.
Okay.
And phase 3?
Phase 3 is heavy element formation, starting around 10 million years after the beginning and ongoing. This is when stars forge heavier elements like carbon, oxygen, iron through fusion.
Standard stellar nucleosynthesis.
Yes, but with a twist. The cosmic water model proposes that some residual cosmic water, maybe lingering in gas clouds, acted as a cosmic catalyst.
Oh, interesting. A catalyst how?
It somehow lowered the energy needed for fusion reactions to happen compared to what standard physics would predict.
Huh? A cosmic helping hand for making elements. So cosmic water wasn't all used up right at the start.
That's the idea, yeah. Now, obviously, a huge piece of this is justifying that 24 billion year age. How do they argue against the standard 13.8 billion?
Yeah, that's the big one. What's the reasoning?
Well, they critique the 13.8 billion figure by pointing out its dependence on the lambda CDM model, our standard model of cosmology. Specifically, its reliance on the Hubble constant being around, say, 70 kilometers per second per megaparsec.
Okay.
The cosmic water model argues the initial energy density, because of all that cosmic water, was much higher than lambda CDM assumes.
And higher initial density leads to an older universe.
How? It leads to a slower expansion rate in the very early universe. After inflation, say, up to maybe the first billion years or so, if the universe expanded more slowly back then...
It would take longer to get to where it is now.
Exactly. Longer to cool down to the CMB temperature we see, 2.7 Kelvin. Longer to form the large-scale structures like galaxy clusters.
Makes intuitive sense. Slower start, longer journey.
Yeah.
Is there maths behind the 24 billion figure in their model?
Yes. You can estimate the universe's age roughly as 1 over the Hubble constant times a factor related to density.
Right.
Using standard values, h around 70, density factor near 1, you get about 13.8 billion years.
So what do they change?
They propose that the effective Hubble constant was much lower in the early universe. Because that high density of cosmic water acted like a brake, slowing things down, they suggest maybe around 40 kilometers MPC initially.
40? That's way lower.
It is. But if you plug a lower effective HA into that age calculation for the early period, you get an age closer to their 24 billion year target.
But changing HA that much must mess with other things, surely.
Absolutely. They acknowledge that. To make it all consistent, you likely need to adjust other parameters too, like the density of matter, or maybe tweak our understanding of dark energy. It's not just one change in isolation.
Right, a whole cascade of adjustments potentially needed. Okay, so let's get into the maths a bit more. They must have some equations for this cosmic water field, right, to make it more concrete.
They do. They treat cosmic water as a scalar field, often represented by phi. Similar to the Higgs field or the proposed Clayton field, it has a value everywhere in space.
And its behavior is described by a Lagrangian. What's that again?
A Lagrangian is basically a function that summarizes the dynamics of a system, its kinetic and potential energy. For this cosmic water field, the Lagrangian dictates how it changes and interacts.
Okay, and what does its Lagrangian look like?
It's fairly standard for a scalar field. There are terms for its kinetic energy, how it changes, and its potential energy, VO. This potential energy function V is really key. Its shape determines how the field evolves and drives everything.
The shape of the potential is crucial. What kind of shape are they proposing?
They suggest a potential with terms proportional to a squared and a to the fourth power. This is a form often used in inflation models because it allows for a period where the field changes, slowly driving inflation, and then decays rapidly, releasing energy.
Releasing energy to create particles, the reheating phase.
Exactly. And they even estimate some values for the parameters in this potential.
Like what?
They put the energy scale around the grand unification scale, maybe 10 AA. Remember, JEB is a huge energy unit for particle physics. The effective mass of the field might be around 10 Na, and a coupling constant lambda maybe 10 AA. These are enormous energies.
It's just huge numbers. So how does this field actually evolve? What's its equation of motion?
It follows a version of the Klein-Gordon equation, adapted for an expanding universe. It describes how oscillates and rolls down its potential energy hill. Importantly, it includes a term with the Hubble parameter, h, which acts like friction.
Friction.
Yeah, it slows the field's roll. This slow roll is needed for inflation to last long enough.
Okay, and how does this field actually create matter?
That comes from an interaction term they add to the Lagrangian. This term describes how the cosmic water field interacts with fermion fields, the fields representing matter particles like quarks and electrons.
Right.
So as mirror oscillates and loses energy after inflation, that energy gets transferred through this interaction, like serratia, into creating these fermion particles. Specifically, they propose it creates primordial hydrogen and oxygen-like particles this way.
So the decay of the field makes the matter.
Okay.
The energy needed, transforming something like water into the entire universe's matter. That must require just colossal amounts of energy.
Colossal is an understatement. The model tackles this by assuming the initial energy density of cosmic water at Planck time was basically the Planck density itself, around 10 air kilograms per cubic meter.
Which is pretty much the maximum possible energy density, theoretically.
Right. So within the tiny Planck's volume, the total initial energy is estimated around 10 air joules. They argue this is enough to create all the universe's matter, around 10 air kilograms in radiation, and fuel the expansion of space-time.
Okay. The energy budget seems plausible if you start with Planck density. What about this aquatic nuclear interaction they keep mentioning? How does that fit the energy picture?
This is a really key but also highly speculative part. It suggests a more direct conversion pathway. Cosmic water, primordial H and O components, elements.
Bypassing some standard fusion steps.
That seems to be the implication. They even give an example calculation, like turning cosmic water into carbon might need about 5.6 GeV per molecule. Summing that up for the whole universe gives a total energy need around 10 degree joules.
Which is roughly in the ballpark of the initial 10 joules they estimated.
Exactly. They argue the initial cosmic water field had enough energy to power this transformation process, however it works.
Yeah.
The mechanism of that transformation is still a big question mark, though.
Right. So energy source,
yeah.
Plausible, mechanism, TBD. Now back to the age. To get 24 billion years, they needed slower expansion. How is that built into the maths with the Hubble parameter?
Okay, so the Hubble parameter, h, its value depends on the energy densities of everything in the universe. Matter, radiation, dark energy, and in their model, cosmic water.
So h squirt 8g3 plus or plus sur plus or, roughly.
Exactly. The key is how the energy density of cosmic water changes as the universe expands, as the scale factor A increases.
And their assumption?
They assume that during this early aquatic nucleosynthesis phase, Ho decreases, like radiation does, proportional to A.
Okay, like photons.
Yes. But because they start with such a high initial rho, this cosmic water component dominates the total energy density for much longer in the early universe compared to the standard model.
And if the universe is dominated by something behaving like radiation for longer?
The expansion rate follows a different pattern. The scale factor A grows proportional to the square root of time. This is a slower expansion than the matter-dominated or dark energy-dominated eras later on.
So that dominant radiation-like cosmic water phase stretches out the early timeline, leading towards the 24 billion years.
That's the core mechanism they proposed for the older age, yes.
Okay, but this model, with its older age and different physics, has to square itself with all the observations that support the standard model. How do they reconcile with things like the CMB, the Hubble constant measurements, galaxy formation?
Right, this is crucial. Let's take the CMB, the cosmic microwave background. It's a cornerstone of the standard model. Its temperature, 2.7 Kelvin, and the patterns in it fit a 13.8 billion-year-old universe incredibly well.
So shouldn't a 24 billion-year-old universe have a much colder CMB?
Logically, yes, that's the challenge. The cosmic water model's explanation is, well, it's that the decay of cosmic water itself released extra radiation early on.
Extra radiation.
Yeah, they propose this extra radiation subtly changed the CMB spectra, made it look like it came from a younger universe. They suggest we need to reanalyze CMB data, especially from Planck, looking for tiny deviations at very small angular scales, high multipoles, 2000. That might be the signature of this cosmic water radiation.
Wow. Okay, so they're saying the signal might be hidden in the fine details we haven't fully resolved or interpreted yet. That's bold. What about the Hubble constant? H,
Yeah.
There's already this tension.
Exactly, the Hubble tension. Measurements of the local universe give H around 73 kilometers MPC, while measurements based on the early universe, like CMB, give more like 67. It's a major puzzle.
How does the cosmic water model weigh in?
Well, remember they need a lower H in the early universe, around 40, to get their 24 billion year H.
Right, so how does that connect to the tension or observations now?
They propose H era wasn't constant. It started low, around 40, consistent with their model's slow early expansion, and then increased over time, maybe due to dark energy, eventually reaching the values we measure today, or perhaps contributing to the difference between early and late measurements.
A variable Hubble parameter.
Essentially, yes. They stress that getting really precise H-arrow measurements at different cosmic distances using JWST, Euclid, Rubin Observatory is key to testing this idea. Can we see H actually changing over cosmic time?
So future observations are critical there. Okay, what about galaxies and stars? Standard model says galaxy formation started maybe 200 million years after the Big Bang.
In the cosmic water model, that slower early expansion actually gives gravity more time to work, pulling matter together. They suggest galaxies might have started forming later, maybe 300 to 500 million years after the origin.
Later start, but maybe more developed earlier than expected.
Exactly. And this, they argue, aligns better with some surprising early JWT results, finding unexpectedly mature-looking galaxies at very high redshifts, Z10.
Those early JWST galaxies have definitely raised eyebrows.
Right. The model claims an older universe provides a more natural explanation for why those galaxies look so developed so early in the standard timeline.
Okay, interesting connection. Finally, element abundances. Big Bang nucleosynthesis, BBN, in the standard model predicts the amounts of hydrogen, helium, lithium we see very accurately. How does cosmic water handle that?
This is a tough one for them. They propose their two-step process. Cosmic water, primordial H and O, then these undergo aquatic nuclear interactions to form helium and other light elements.
Aquatic nuclear interactions, that still sounds pretty hand-wavy.
It is mechanism-wise. They don't have a detailed physical model for it yet, but to test it, they suggest looking at isotopic ratios in very old gas clouds.
Isotopes, like deuterium.
Exactly. Things like the deuterium to hydrogen ratio, DH, or oxygen isotopes. They predict their unique aquatic processes might leave a different isotopic fingerprint compared to standard BBN. Analyzing pristine, high redshift nebulae could potentially reveal these differences.
Okay, so subtle chemical signatures as potential evidence, right? This is all fascinating theory and interpretation, but science needs tests. Does the model propose specific experiments to prove or disprove it?
Yes, and this is crucial for any scientific theory. They outline several potential tests. First, going back to the CMB, the goal is to find those predicted subtle deviations caused by the X-ray radiation from cosmic water decay.
How do we look for something that subtle?
With next-generation CMB experiments, things like the Simons Observatory, CMBS-4, these are designed for incredible sensitivity to temperature and polarization fluctuations. The hope is they'll spot tiny anomalies, maybe unexpected peaks or shifts in the CMB power spectrum, especially at those very fine scales, the high multipoles. They think results could come in 5-10 years.
Looking for tiny wrinkles in the universe's baby picture. Okay, what's test number 2?
Measuring the Hubble constant, H, throughout cosmic history. The objective. See if it really was lower, around 40 kilometers MPC, way back then as their model requires.
How do we measure H's billions of years ago?
By combining different techniques. Using JWST to observe very distant supernovae, high redshift ones, and using data from large surveys like Euclid and Rubin LSST that measure gravitational lensing, how gravity bends light from distant objects. Putting these together can map the expansion rate over time.
And the expected result?
Evidence for a lower H at high redshifts, say Z5. That would support their slower early expansion idea. They think we could get meaningful results here in maybe 3 to 7 years.
Cosmic archaeology, digging into the expansion history. What else?
Third, really deep galaxy surveys, pushing beyond current limits to confirm if those surprisingly mature galaxies exist at even earlier times, maybe at redshift Z15.
Even earlier than the ones JWST is already finding.
That's the idea. Using JWST's NIRCam to find them and then analyze their light to measure metallicity, heavy elements, and star formation rates. If they find galaxies that look chemically evolved and must have taken, say, over 500 million years to form, that fits much better in a 24 billion year timeline. Initial results could be relatively quick, maybe 2 for 5 years.
JWST is really central to a lot of these tests. Any other angles?
Fourth is the isotopic analysis we mentioned, looking for direct chemical fingerprints of those hypothetical aquatic nuclear interactions. Using ALMA, the radio telescope array, to measure isotope ratios like DH and RO with high precision in very old, pristine gas clouds at Z3, if they find ratios significantly different from standard BBN predictions, that would be strong support. This needs very careful measurements, maybe a 5-10 year timescale.
Searching for specific chemical fossils, and the last test involves computers.
Yes. Number 5 is cosmological simulation. Basically, build a virtual universe based on the cosmic water model's rules, the initial conditions, the slower expansion, the field itself.
See if the simulation looks like the real universe.
Exactly. Modify existing simulation codes like Gadget or APO, run them with the cosmic water parameters, and see if they reproduce the observed large-scale structure, galaxy distributions, and CMB properties over 24 billion years. This could also reveal unique features of such a universe to look for. Developing and running these simulations might take 3 to 5 years.
Okay, that's a pretty thorough test plan. CMB, H's history, early galaxies, isotopes, simulations. They seem serious about making this falsifiable. Now, looking at the model itself, what do they see as its main strengths?
They highlight a few things. First, that alignment with the early JWST results the surprisingly mature galaxies. They argue their older timeline just makes more sense of that observation.
Yeah, that's definitely a hot topic right now. What else?
Second, they mention a kind of a philosophical appeal. The idea of water being fundamental connects with some very old human ideas and myths about creation. This model tries to put that intuition on a scientific footing.
Interesting. A resonance with ancient ideas.
Perhaps. Third, they point to the model's flexibility. By adjusting parameters related to cosmic water, they hope it might provide a better fit to various cosmological data points, maybe even resolving existing tensions like the Hubble issue. It offers an alternative framework.
And four.
Its testability, which we just covered, having multiple independent experimental pathways to check the model, is a major strength. It means it's not just speculation. It can be scientifically evaluated.
So, addresses some puzzles, has philosophical echoes, flexible, and testable. Okay? But every new idea faces pushback. What are the big challenges for the cosmic water model, and how do they respond?
Well, the biggest is probably the CMB. As we said, it fits the 13.8 billion year standard model so well.
How do they get around that strong evidence?
Their main counterargument is that hypothetical extra radiation from cosmic water decay. They claim it alters the CMB just enough to mimic a younger universe, and that future, more precise CMB experiments will eventually uncover the difference, revealing the true older age.
That's putting a lot of faith in future experiments finding exactly what they predict. Okay, what's another hurdle?
The lack of a clear physical mechanism for that aquatic nuclear interaction. How does cosmic water actually transform directly into elements? We just don't have physics for that right now.
Yeah, that feels like a pretty big gap.
They acknowledge it's hypothetical. Their response is essentially that the details might emerge from future developments in more fundamental physics, like quantum gravity or string theory. Maybe those theories will reveal new kinds of interactions possible only in the extreme early universe.
So it's an unknown, but maybe future physics will explain it kind of answer.
Pretty much. And the third main challenge.
The Hubble constant again. Current measurements mostly point towards the younger age, conflicting with the 24 billion year requirement.
Right. And their response, as we discussed, is that H isn't constant. It was lower early on, around 40, and increased over time.
The variable H idea.
Exactly. They argue that measuring H precisely at different distances, different cosmic epochs, is the way to test this. If H is found to have been significantly lower in the past, it supports their model. If not, it challenges it.
So again, future observations are key to resolving these major challenges. The source material also mentions some more speculative ideas, extensions of the model, multiverses, cosmic memory.
Yes, it definitely goes into some far-out territory there. The multiverse idea suggests cosmic water isn't just our universe's source, but maybe it's recycled between multiple universes.
Oh.
Speculatively, through things like theoretical wormholes or quantum tunneling between universes, or maybe within string theory's brain world scenarios where cosmic water could be a fundamental entity spanning different dimensions or brains.
Wow. Okay. Definitely pushing the boundaries there. What about cosmic memory?
The idea here is that cosmic water, maybe in its quantum state, could somehow carry information from previous universes or cosmic cycles, and maybe we could detect faint traces of this information as specific kinds of subtle irregularities called non-Gaussianities in the CMB.
Looking for echoes of past universes in our CMB. That's wild.
It's a very speculative but fascinating idea. And finally, they also refine how cosmic water's energy density evolves.
How so?
They stick with the idea that it decreases like radiation, proportional to Oyo, as the universe expands. But because it started so high, it dominated the energy budget for longer, extending that radiation-like era, which helps achieve the older age without messing too much with the later matter and dark energy-dominated eras.
Okay, it makes sense within their framework. Now, towards the end, the material connects this scientific model to excerpts from another text. So, cosmic water. What's that connection about?
Yeah, this part tries to link the scientific model we've been discussing with ideas from a text that approaches creation from a faith perspective, specifically drawing on the Quran.
Citing verses from the Quran.
Yes. Surah Al-Anbiya 21.30, which talks about heavens and earth being joined then separated, and crucially, we made from water every living thing. And Surah Hud 11.7, mentioning creation in 6 days and God's throne being upon water.
So, drawing a parallel between the Quran's emphasis on water's fundamental role and the cosmic water model's central idea.
Exactly. The Chonche Set text apparently views water as foundational, maybe even part of a cosmic control system. It mentions 10 dark stages before light, which the model's authors see as potentially mapping onto early phases in their own cosmology.
Interesting overlap in concepts, even if the approaches are different. Does the Chonche Set text also talk about the universe's age?
Yes, apparently it suggests the current scientific age estimate is wrong, aligning with the cosmic water model's 24 billion year proposal. It even contains a simplified calculation about the huge energy needed to turn water into elements, a problem the scientific model tries to solve with its high-energy primordial cosmic water concept.
So convergence on an older universe and water's importance, but from very different starting points, faith versus a scientific model.
Precisely. The source material stresses that while Qassafi uses faith and revelation, the cosmic water model aims for a scientific framework with maths and testable predictions. The refined model builds on these initial thematic links, firming up its postulates, citing supportive evidence like Gupta's model or JWST data, detailing the math, and enhancing the experimental tests.
So the scientific model tries to formalize some of those core ideas, and the experimental tests got refined further.
Yes, the refined plan gives more specifics. Looking for certain polarization patterns and non-Gaussianities in the CMB with next-gen telescopes pushing for higher precision H measurements over cosmic time, deeper spectroscopy of ultra-high redshift galaxies, more detailed isotopic analysis with LMA and SKA, more sophisticated simulations including the cosmic water field, and even looking for theoretical consistency checks within string theory.
Really comprehensive research program. And they also map out how to get the model taken seriously by the scientific community.
Yeah, standard scientific practice, really. Publish in peer-reviewed journals, collaborate with experts in cosmology, particle physics, astrophysics, do outreach, seek funding for the proposed experiments, and share data openly for transparency and independent checks.
All the right steps for a serious scientific push. They clearly believe this model has the potential to be transformative.
Absolutely. They circle back to its strengths, aligning with some new observations, potentially resolving existing tensions, and having a clear path forward for testing. Those are the key next steps they see.
Well, this has been a really deep dive into the cosmic water model. Just to recap for everyone listening, we've looked at a theory proposing a much older universe, 24 billion years, originating from a primordial, energetic cosmic water.
We explored how it suggests this water transformed into matter, energy, and space-time, its mathematical underpinnings, and how it tries to fit with observations, sometimes by reinterpreting data or predicting future discoveries.
And we covered the extensive list of experiments proposed to test it, from CMB details to distant galaxies to isotope ratios.
It definitely challenges the standard picture and makes you think.
It really does. It sparks those aha moments. forcing you to consider radically different frameworks, and connects cutting-edge science with some surprisingly ancient ideas about water's role.
And it highlights that cosmology is still very much a work in progress. Our current understanding is powerful, but maybe not the final word.
Which leaves us with a final thought for you. Could our picture of the universe be fundamentally different? What if water, in some ancient powerful form, really was there at the very beginning? Something to ponder. Thanks for joining us on this deep dive.
أنا دكتور خالد وليد، ربان سفينة النجاة إلى شواطئ بكة القدس. I am Dr. Khaled Waleed, the captain of the ship of salvation to the shores of Baka, Jerusalem.